Okay, so these are our notes. I think we're on about the 4th page here for 10.8 graphing polar functions. And next up, we are going to talk about something called a rose curve. So at the top, we have the general sort of formatting for a rose curve. You're back down to a single sine or cosine, single term. You have a constant times either sine or cosine. But on the inside, rather than having just a theta, that would be a circle, we have a number, n, times that theta. And what this will do is it will generate for you sort of a flower shape. If you have that pink sheet in front of you that we passed out, right, we're looking at rose curves in the middle of that sheet, and you can generate these flower petals as part of your function. It's pretty cool. They look pretty neat. There are some cool shortcuts or quick shortcuts on how to graph them. They're pretty easy, actually. So we want to start just with the basic rules. You want to focus on whether or not n is going to be even or whether it's odd. And, if n is greater than or equal to 2. If n is an odd number, then you know that you will have n petals. So for example, I can glance at the top 2, and I know that I will have 3 petals and I will have 5 petals. If n is even, then you'll get double the number of petals. So 2 times n. So for example, in letter C, I can look at this quickly and say, oh, this is going to have 8 petals. This one will have 4 petals. So it gives me an idea of sort of the shape of the graph. The other thing that you can do is take advantage again of your symmetry. So let's work on one together. If I glance at this one here, r equals 2 times the cosine of 3 theta, I know that the symmetry is going to happen over the polar axis. And because n is 3, and 3 is an odd number, then I know that I will have 3 petals. Your petals are always evenly spaced in the plane. So if you think of a full cycle as being 2 pi, or sometimes on these problems, it's much easier to think in terms of degrees. So oftentimes you'll work maybe in degrees or radians, depending on sort of what the problem is. But a full cycle around is 2 pi radians, and I need to fit 3 petals evenly spaced into that. So my petals, their points, if you look at our examples of what a rose curve looks like, the tip of that petal, the tip of this petal, we could measure the angle between them, and it would be equal to 2 pi over 3, right? So this is a full cycle, and I want to divide it into 3 petals. So I know that my petals will be 2 pi over 3 radians apart. And the other thing that I can see just from the formula is that my A value is 2. So this is the petal length. Now, when I'm working with cosine, because of my symmetry, I know that that petal length is going to happen on the x-axis. So I will have a point right here. And that would be sort of the tip of one of my petals, because I am going to draw it something like this. And that would give me 1 petal. I would have the symmetry over the polar axis. Now I need to space them so that those tips of my petals are 2 pi over 3 apart. So in cosine, if I know that the first one started at 0, then the next one should be at 2 pi over 3. So at 2 pi over 3, I should have another petal that is at its tip, and it would be right about here. And another 2 pi over 3 would bring me to 4 pi over 3. So the tip of the last and the third petal would be right here, going towards 2 pi over 3 and 2 units in length. And so my flower will look something like that. Now on the rose curves, I don't spend a lot of time plugging values into my calculator. The only thing I really need to find would be those tips of the petals, and then the spacing helps me draw them. Cosine is a little bit easier because it always has that symmetry around the axis, or around the polar axis, I should say, and it will always start so that the tip of the first petal is on the sort of positive side of that polar axis. The reason for that is because if theta is 0, right, then the cosine of 0 would be 1, and 2 times 1 is 2. So I'm guaranteed to have sort of that furthest distance away right on the positive half of that polar axis. Let's try this one, right? This is also a cosine function. I can see that it's r equals 3 cosine of 4 theta. I know because it's a cosine function that it will be symmetric over the polar axis. And actually, this one will have some more types of symmetry too. Because n is even, because n is equal to 4, this time I'm going to have 8 petals. So that means that my 2 pi radians, over that course of a full cycle, I need to be able to have 8 petal points, and my tips of my petals will be pi over 4 apart. Their length will be 3, because the A value is your petal length. So A equals 3, that is the petal length. And I'm going to draw my first one on the x-axis, right? The next one should be spaced pi over 4 apart. So at pi over 4, 0 plus pi over 4, I would again have a coordinate 3 units out in that direction. Right? Pi over 2 would be another pi over 4. I'll have one at 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and 7 pi over 4. So those 8 dots are going to become the tips of my petals, and I can just sketch it in. It'll look something like this. The rose curves are always kind of fun to sketch in. So that is an example where I have 8 petals. Notice on this one, I am also symmetric about the theta equals pi over 2. That's just by chance because of the way that my petals were spaced. But the one that was sort of guiding my initial work was the polar. Sine is a little bit different. So let's work on sine next. This time, I'm going to have symmetry over theta equals pi over 2. And so the trick here is that sort of the easiest one to plug in is theta equals pi over 2. That would give me a length of 3. I should have a petal that is 3 units long. I should have a point 3 units from the pole that goes in the direction of pi over 2, just simply by plugging values in. On this one, n is an odd number, and therefore I know that I would have 5 petals, each of a length of 3. The trick is that I need to take and separate them out 2 pi over 5. So within a full cycle, within 2 pi, I need to go and work at a 2 pi over 5 increments. I need to move over 2 pi over 5 4 more times to wrap my way around the circle. Unfortunately, fifths aren't really helpful in terms of graphing. So this is an example where I would probably just have an easier time converting over and thinking about them as being 72 degrees apart, because it's easier to visualize what's happening, right? If you are at a 90-degree angle, then 72 degrees to the left, if I rotate this way, then I should be at 18 degrees. So if we think about this as being 30, then 18 is going to put me somewhere around here. And on that radial, I want to go out 3 units. Likewise, right, I would rotate 72 degrees this way. That's going to put me, right, and I can use symmetry, or I can think about exactly how to measure it, but that's going to put me right about here. And you might want to just grab a calculator. I think what I did was, when I first did this one, I thought of it as, okay, well, I'm at 90, and I'm going to add 72 degrees to get to that coordinate. So that would be at 162 degrees. I would need to rotate to the next one, so that's another 72-degree rotation. 234, it's probably somewhere down here. I'm not going to measure it out. You don't need to have it perfect. Symmetry about the y-axis would mean that I would, again, have a point here and a point here. So in those 5 directions, right, I would have my 5 petals. And then I can go ahead and sketch in my curves. I'm not going to find 20 more points to sketch in. So that one's a little different. I'm starting here. when you have an even, sine gets even more tricky. So the symmetry is again going to be over theta equals pi over 2. However, with an even number, my petals don't end up starting right at the center. Because think about it, if I want to plug in a pi over 2, then what's going to happen? I would actually end up at with a 0, right? Because if theta was pi over 2, 2 times pi over 2 is 1, or sorry, it's pi, and I would get sine of 0. So that would actually put me just at the pole, and it wouldn't help me. If my multiplier is 2, then what angle do I need to plug in order to get to pi over 2? I actually need to plug in pi over 4. So one way of thinking about these problems is to think about solving, where is my sine of 2 theta going to be the largest? Well, it's going to happen when the sine is equal to plus or minus 1, right? That would give me either a 4 or a negative 4. So where does that happen? It happens when 2 theta is equal to, well, sine is equal to 1 at pi over 2, negative 1 at 3 pi over 2, and I could keep wrapping around the unit circle. So 5 pi over 2 and 7 pi over 2 and so on. Maybe you remember solving these multiple angle formulas back in an earlier chapter, back in chapter 5. That would mean then that theta, if I divide both sides by 2, would be at pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. So my petals, right, I know that I have an even n value. I should have 4 petals, and they're going to show up at these values. So pi over 4, right, I should go out 4 units. So 1, 2, 3, 4 on that radial. 3 pi over 4, 1, 2, 3, 4. 1, 2, 3, 4. And likewise over here. So my petals will look something like this. So they're not centered right around, but I still do have that symmetry. That's going to happen when you have a sine of an even number. Okay. You do want to be a little bit careful. I think I might have misspoke up here. We're not plugging in pi over 2 necessarily. When I plug in pi over 2, I'm getting the sine of 5 pi over 2, which is itself coterminal with that pi over 2. So we could have kind of done the same thing down here and solved for our values. That takes us really nicely into the very, very last page of our notes. So I am going to start another video just to keep them a little bit shorter. This one will just be about roses. We'll talk maxes and mins in the next one.